Last video, we built a DIY accelerometer using a McIntosh apple hanging from a spring scale. We used it to estimate how far an elevator traveled from the first floor to the fourth. From the apple's motion, we calculated 16 meters. But when we measured the building directly, using photographs and rulers and stairs, we got 14.5 meters. It was okay, but not exactly right. So today, we're going to find the cause and fix the experiment properly. Before we blame the McIntosh we used, remember what we're measuring: acceleration. So we have to consider everything that's being accelerated in our system. The first question, did we forget the dish? Nope, the 102 grams in the original video included both the apple and the dish. But now, take a second and look more carefully at the setup. There's another part of the system that's also affected by the elevator's motion: this blue indicator and needle assembly. In the original analysis, we didn't include its mass. You might say, but the scale is zeroed with that blue part attached, so we can forget about it, right? Yes and no. And that's exactly why we missed something important. Typically, when a mass hangs from a spring under gravity, it settles to a resting position. We usually define that resting position as the origin, or zero, so the device's mass is effectively cancelled out. That works in most cases, but when the elevator accelerates upward by A, the device accelerates upward too, so the spring feels an extra force and stretches further. That extra m times A contribution is what we forgot. So at this point you might think, okay, let's open up the scale and weigh the blue part. And sure, we could do that. But no, we're not going to sacrifice a perfectly good tool for measurement. There are things other than the blue part that matter. Remember, any real spring has mass. We usually model it as a massless ideal spring, but to be exact, we have to consider its dynamic or effective mass, meaning the part that contributes to the motion. And this dynamic mass is different from the spring's total mass, because different parts of the spring move different amounts. Look at this familiar example. When you're measuring acceleration, you need the effective dynamic mass of the whole system. And here's the most important part of the whole video. Dynamic behavior requires dynamic measurement. So instead of taking the scale apart, we let the system oscillate. A mass spring system naturally oscillates as simple harmonic motion. Now, it's time to learn the theory. Newton's second law plus Hooke's law gives us the basic equation for a mass on a spring. Next, we divide by the mass to put it in a simpler standard form. To solve this, we assume a solution of the form x of t equals e to the lambda t. When we plug equation number 2 into equation number 1, we get a condition on the exponent. It comes out imaginary. The Euler's formula tells us that the motion is an oscillation. The general solution can be written using complex exponentials. But what we actually observe is the real measurable part: a sine function with some amplitude and phase. From that, we identify the angular frequency of the phase and then convert it to the regular frequency. F equals 1 over 2 pi times the square root of k over m. Whatever the derivation, what we need for today's experiment is just these two equations: the simple harmonic motion equation and its resonant frequency. In the first experiment, the apple and the dish were 102 grams together. So, we rebuilt it in the most scientific way possible. We grabbed another apple, took a bite, and trimmed it until it was exactly 102 grams again.
Oh my God!
This will do. The scale has an uncertainty of about plus or minus 1 gram, so 101 grams and 102 grams are not meaningfully different on this scale. We're not trying to hide the fact that we took one bite too many. Now the apple is ready. Let's observe the oscillation. Here, we did the image analysis. We tracked the motion of the hook relative to the scale body. The oscillation shows up as a clear sine wave. You may also notice the decay. We can talk about that another time. There are many ways to find the frequency from this data. Here, we detect all the peaks in the graph. The time from one peak to the next is one cycle. We repeat that across the whole sequence and calculate the frequency. and we find the frequency to be f equals 2.93 Hz. Now, let's find the dynamic mass. We've measured the frequency, so we just need k to find m. The spring scale's calibration gives us the spring constant. On this scale, 1 Newton stretches the spring by exactly 1 inch. It's a funny mix of SI and inches, but 1 inch is 0.0254 meters, so K equals 39.37 newtons per meter. Now we know both F and K, so we're ready to find the dynamic mass M. We plug them into the frequency formula, and solving gives M equals 0.116 kilograms or 116 grams. Let's summarize. Previously, we only counted the apple and the dish, set to 0.102 kilograms. But we forgot the blue indicator, the spring's effective mass. Oh, and we also forgot the hook. We should have included all of them. The video clearly shows that they all move with the oscillation, and the total effective moving mass comes out to 0.116 kilograms. Here's Newton's second law again. We measured F from the experiment, but we underestimated the mass. We used 0.102 kilograms, and now we found that it should be 0.116 kilograms. So, the correct acceleration has to be smaller than what we calculated before. Let's do the analysis again with the updated total dynamic mass. As you can see, the magnitude of the calculated acceleration becomes smaller. Now, both the velocity and the height become smaller accordingly. Let's check the updated result. The calculated height is 14.1 meters. And do you remember the estimated building height was 14.5 meters? Is that close? What do you think? We started this as a fun project, but now we really want to see how accurate our Apple accelerometer can be. So next time, we'll take a more serious scientific approach, revisit the setup, and track down the remaining sources of error. And yes, there will probably be another Apple.